everybody, we are from Group 2, Section 1. Today, we will be presenting the flash separator design. My teammates consist of myself, Ivashni, Cedric, Alisha Farhana, and Lukman. Flash separation is a technique used to separate liquid mixture into its liquid and vapor components based on its differences in polarity or boiling points. It occurs due to a pressure drop, causing a portion of liquid to vaporize or flash into vapor. This process is widely used in various industries, such as the petrochemical industry for petroleum refining and natural gas processing. A mixture of methanol and water is miscible, which means it can completely mix together in all proportions. The hydroxide group in both methanol and water can form hydrogen bonds with each other. The objective of our project is to design a flash for separating a mixture of methanol and water. Next, we will review the overall composition, operating pressure, and temperature for separating the mixture. The following calculation will be done by assuming that the reaction mixture is an ideal solution. We will be calculating the moles of liquid, moles of vapor, liquid phase mole fraction, and vapor phase mole fraction.
The problem statement of this project is to design a flash separator for a mixture of methanol, species 1, and water, species 2. The assumption made is the mixture is an ideal solution and it is in a steady state condition. The basis is 1 mole of mixture. We also assume that the overall composition of methanol is 0.65, whereas the composition of water is 0.35. The temperature assumed is 75 degrees Celsius, while the pressure assumed is 0 kilopascal. By using the Antoine equation and substituting the relevant parameters in the equation, we can calculate the saturation pressure for both methanol and water. It is found that the saturation pressure for methanol is 149.92 kilopascal, while for water it's 38.64 kilopascal. And then, we need to calculate the bubble point pressure, which is the pressure at which vapor starts to form in the liquid, and the dew point pressure, which is the pressure at which water vapor will condense back into liquid. At bubble point and dew point, the mole composition of a species in the liquid and vapor form is the same. So, we substitute the compositions and P saturated calculated before into the bubble point and dew point equations, and we obtain P bubbles equals to 110.97 kilopascal and dew point pressure is equal to 74.66 kilopascal. Flash calculation can be applied when the pressure of a system lies between the bubble point and dew point. Under these two conditions, the system exists as a two-phase mixture of liquid and vapor in equilibrium. This allows for the calculation of vapor phase, vapor fraction, and the composition of both liquid.
So for the first step of the flash calculations, which is the calculation for the equilibrium ratio Ki, so we have the formula which is Ki, which is equivalent to Pi saturated over the P system. So we will calculate for K1 and K2. So for K1, which is equal to P1 saturated over P system. So for the P1 saturated that we calculated is 149.9158 kilopascals, and for the P system that we set it's 100 kilopascal. So from that, we'll get a value for the K1 is 1.4992. As for the calculation for K2, K2 is equivalent to P2 saturated over the P system. So for the P2 saturated that we got, it's 38.6403 kilopascal, and for the P system is also the same, which is 100 kilopascal. And from there, we'll get a value of K2, which is 0.3864. So now we move on to the second step of the flash calculations, which is the calculation for the mole of vapor phase V. So we have the formula, which is the summation of Zi Ki over 1 plus V times with Ki minus 1, which is equivalent to 1. So from here, we can see that for the both of the components, we will try to find the value of V, which is also equivalent to 1. But since that the trivial solution will be obtained when V equals to 1, therefore the trial and error method is used to obtain a value of V which is between the range of 0 and 1. Hence, by using the trial and error method, we can get a value of V which is equivalent to 0.3582, which also allows the summation to be also equivalent to 1. Therefore, by obtaining the value of V, which is the mole of the vapor phase, which is equivalent to 0.3582 mole, we can also obtain the mole of the liquid phase L by using the formula L equal to 1 minus V, which is also equivalent to 0.6418 mole. Now, we'll move on to the next step of the flash calculations, which is the calculation for the mole fraction of vapor phase Y and liquid phase X. So for the vapor phase, we will calculate for the two components, which is Y1 and Y2. So for Y1, which is for methanol, so Y1 is equivalent to Z1K1 divided by 1 plus V times with K1 minus 1, and we will obtain a value of Y1 of 0.8267 mole methanol per mole. As for water, which is y2, which is equivalent to Z2K2 over 1 plus V times K2 minus 1, where we'll get a value of 0.1733 mole water per mole. So that is the mole fraction for the vapor phase. As for the mole fraction for the liquid phase, there is the formula, which is x1 equivalent to y1 divided by k1. So from there, we will get the x1 value of 0.5515 mole of methanol per mole. As for x2, we will also use the same formula, which is equivalent to y2 over k2, where we'll get the value of 0.4485 mole water per mole for x2. So that is for the mole fraction of the liquid phase.
I will present the graph of composition of methanol in vapor x1 and liquid y1 against pressure at 75 degrees Celsius. First, we need to determine the values of x1 and x2 from the range of 0 to 1 with the interval of 0.1. Then, we calculate the pressure within kPa using the bubble point pressure. Then, we can calculate the value of K using Rhodes' law, which is P saturated divided by P. Lastly, we determine the value of y1 by multiplying x1 by k. The steps are repeated for each x until x is equal to 1. This is the graph of Pxy calculated from the table previously. We can see that the values of x1 and y1 increases linearly with pressure. After the point of intersection between x1 and y1, the component only exists in one phase and no liquid-vapor equilibrium exists between the component. The calculation of Pxy graph was done using Excel. First, we need to set pressure at 100 kPa to determine the correct temperature. Then, we input the liquid phase mole fraction of methanol and water, which is x1 and x2. Then, we calculate the saturation pressure for both methanol and water using Antoine's equation. The values of K1 and K2 are calculated by dividing P saturated by P. Then, the values of y1 and y2 can be calculated by multiplying the values of x1 and x2 respectively with K1 and K2. Then, we sum up the values of y1 and y2. We can see that the summation is not equal to 1. Therefore, we will need to use the goal state function on Excel to change the value of y1 plus y2 equals to 1 by changing the temperature given. So, for x1 equals to 0 and y1 plus y2 is equal to 1, the value of temperature is 99.63 degrees Celsius. The data calculated using Excel is summarized in this table. With temperature on the y-axis and x1 and y1 on the x-axis, the graph of Txy can be computed. This is the Txy graph computed from the table previously. We can see that the composition of x1 and y1 increases when temperature decreases. The system only consists of methanol and liquid and vapor phase at around 337 Kelvin.
For the actual moles of vapor and liquid, we assume the feed amount is 1 mole of solution of methanol and water mixture. For the moles of vapor, we use the vapor fraction, and we multiply it with the feed to obtain 0.3582 moles. And for the liquid, we use the liquid fraction, which is now 0.6418 moles. So this shows the flash separator vaporizes approximately 35.82% of the feed. For the percentage recovery, we focus on the methanol recovery in vapor phase, which is given by the formula Vy1 over Z1 times 100%. We obtained 45.5% methanol fed into the system was recovered in the vapor product. To conclude, we start with the summary of key results. The flash separation of the methanol water mixture at 100 kPa successfully demonstrated the principles of vapor-liquid equilibrium. Methanol, being the more volatile component, was enriched in the vapor phase with a mole fraction of 0.267, where the water mole fraction of the liquid was 0.4485. The vapor and the liquid fractions were 0.3582 and 0.6418 respectively, which indicate partial vaporization of the feed. The recovery of the methanol in the vapor stream was approximately 45.5%, confirming the separator's capability to shift the product compositions through thermodynamic equilibrium. Flash separation is relevant in industry as they are widely used in the chemical and petrochemical industries due to their simplicity, low energy consumption, and effectiveness for mixtures with moderate volatility differences. They are commonly applied in crude oil distillation, natural gas processing, and alcohol purification. The methanol water system in particular is relevant to biofood productions and pharmaceutical industries, where the phase separation plays a crucial role in downstream purification. For the possible improvements and consideration, for this assignment, we assume ideal behavior using Rhodes' law and Antoine equations to estimate vapor-liquid equilibrium. Under this assumption, interactions between all molecular species are considered equal, and no deviations from ideality are expected. This simplifies and allows straightforward calculations. For the non-ideal system, however, the methanol-water mixture is known to be strongly non-ideal due to the hydrogen bonding and significant differences in molecular interactions. So to better represent real behavior, future work could incorporate activity coefficients using models such as Wilson, NRTL, or UNIQAC, where these models adjust for non-ideal interactions in the liquid phase and provide more accurate VLE predictions. Furthermore, using simulation tools such as Aspen Plus or performing experimental validation would enhance the reliability of the design, especially for industrial scale application where precision is critical.
Last but not least, these are the references used to assist on our findings, and that's all from us. Thank you.